Okay, so good everybody. So we'll start. Today we discuss the binary relation. Okay, so suppose let S be a non-empty set and a relation we know relation is a basically. So, we know the Cartesian product S cross S, this is basically ordered pair where A, B are both coming from S. This is called Cartesian product. Now, any subset of this Cartesian product is called binary relation, any subset of this Cartesian product. So, a relation is a relation. Here we have only one set. So, that is why it is called binary relation. Relation is a subset of S cross S. So, if we denote the relation by rho, rho is basically a subset of S cross S. Okay. So, now if so this is subset of S cross S. Now, if we take an element from S cross S, it is either belongs to rho or not belongs to rho. So, suppose we take an element from S cross S. Okay. Now, it is either belongs to rho or it does not belongs to rho. So, now and suppose it is and A B is belongs to rho, then what we can say? We say that A is related to B, A B are related under the relation rho, or in other word we write A is the element A is related or A is having relation with the element B, that relation is rho, I mean having the relation rho with the element B. In other word, A is said to be related to B. A is related to B. Okay. So, this is the this is if A B R belongs to rho. Now, if A B R not belongs to rho, then this is A is not related with the B. So, then A is not. So, A is not related to B with B. If A B is not belongs to this rho. Okay. Now, we can take some example, very common example like if we have a human population, S is they said all human being, and then if we define the friendship relation. So, if you take all the people, S is the human population at say IIT KGP. So, we are talking about a population human being, all the people at IIT KGP. Now, we take A B, we say A B belongs to rho if and only if and only if A is a friend of B. We take two human, say Saurabh and Palas. Now, we say A B are related, A is related with B if they are their friend, that is a relation. So, this way we can define a relation. So, it is basically a subset of S cross S, because if you take any two element, then it not be a friend. So, this is a subset of this. Okay. Now, if we take another example like any subset of this Cartesian product is called binary relation. So, if we have say 1, 2, 3, 4, we know the S cross S is all possible pairs 1 1, 1 2, 1 3, 1 4, 2 1 like this. But if we have a relation like this 1 1, 2 2, 3 3, 4 4, we can have this is also, this is basically a subset of S cross S. Any subset of the Cartesian product is called a relation, called a binary relation, any subset. Okay. So, now we can have another example like on Z. Suppose we want to define a relation on set of integer Z, binary relation. So, we define the row as follows. This is a subset of the Cartesian product such that A plus B is say even number. If A plus B is even, then we say A is related to with B. Okay. So, then who are the member in row? So, if you take 1 1, 1 1, if we add, it is 2, 2 is even number. Then 1 3, 1 5 like this, 2 2 like this. But if we take 1 4, this not belongs to row, because 1 plus 4 is 5, 5 is not an even number. So, this does not belongs to this relation, and this is a subset of the Cartesian product. So, any subset of the Cartesian product will give us a relation, different relation we can have. Okay. So, now this is a binary relation. Now, we define what do you mean by equivalence relations. So, for that we need to define three types of relations: reflexive, So, suppose we have a set non-empty set S, which is, and we have a relation rho, which is a subset of S cross S. Now, we say this rho is reflexive. We call the relation rho binary relation. Rho is reflexive if and only if AA belongs to rho for all A So, basically A is related with A is related with A, and this must be true for all the members. So, every member is related with itself under this relation rho. Then we call this relation to be reflexive, like friendship relation. We define the friendship relation. So, this is a reflexive, we can say, because I am a friend of myself, that way. I mean, now equality relation, if we define a relation say over R or even over Z, then equality relation. Now, 1 is equal, every number is equal to itself. So, this is a reflexive relation. Even we define the relation like this one, A B coming from Z cross Z, such that A plus B is even. This is also reflexive, because if what is A is basically A plus A plus A is 2A. So, 2A is always even. So, A must belongs to this for all A. So, this is a reflexive relation. Okay. Now, next one is symmetric relation. We called a relation rho is symmetric if it satisfies some property. What is that property? This is symmetricity or symmetric relation. Rho is called symmetric if suppose AB belongs to rho implies BA belongs to rho. Suppose we take an element from the row AB, then BA has to also belongs to rho. So, this means A is related to B imply B must related with A. Okay. So, this is called reflexive relation, symmetric relation. So, like equality, if we take S to be say R, set of all real number, and if we take the relation like rho is basically A comma B belongs to R cross R if A is equal to B. So, this equality is a symmetric relation, because if A is equal to B, that means B is equal to A. So, that means if AB is belongs to rho implies BA is belongs to rho, this is quite obvious. Even friendship relation is also symmetric, because if I am a friend of you, you are also friend of me. So, friendship relation is also a symmetric relation. Okay. So, now which one is not symmetric relation? Like this one, like less than. If we define a relation say on R, A B belongs to, this is coming from the Cartesian product, if A is less than B. So, that means 1 3 belongs to this row, because 1 is less than 3, but 1 3 belongs to row does not imply 3 1 belongs to row, because 3 is not less than, but 3 1 does not belongs to row, because 3 is not less than 1. So, this is not a symmetric, this is not satisfying the symmetric property. So, this is not a symmetric relation. Okay. So, now we define another type of relation which is called transitivity. This is the properties of the relation. The third one is called transitive or transitivity. A row is called, a relation rho is called transitive if we take element A B from row and B C from row. We take two elements, one is A B, another one is B C from row. If this implies A C belongs to row, then this relation is, and if it is true for all such A B C, if it is true for all such A B C, Yes. So, earlier also for symmetric also, if it is true for all that A B. Now, here also if we take two element A B and B C, if A is related with B and if B is related with C, now this both should imply A is related with C. Okay. Then this relation is called transitive relation, or this property is called transitivity. Now, for example, this less than, if we define a relation say less than like this over R, R cross R, where A is less than B. Now, this is a transitive relation, because if we take A is related to B, that means A is less than B, and if you take B is related to C, that means B is less than C. Now, this both implies A is less than C. So, that means A is related to C. So, this less than or less than equal to, greater than equal to, equality, all are basically transitive relation. Okay. So, now which one is not a transitive relation? Like friendship, friendship may not be a transitive relation. If I am a friend of you, you are a friend of him, that does not mean that I am friend of him. Okay. So, this is not a, this may not be a transitive relation, need not be a transitive relation. Okay. Then we can have, so if these three properties satisfy for a relation, one is symmetric, reflexive, symmetric, transitive, then we call the relation to be equivalence relation. That is the definition of equivalence relation. So, let us define the equivalence relations. Equivalence relation. So, what is the definition? So, if a relation is called equivalence relation, if it is reflexive, symmetric and transitive. A relation, a binary relation rho is called an equivalent relation if rho is reflexive, symmetric and transitive. Three together must satisfy. All of three must satisfy. If one of these is not satisfying, then then the row is not an equivalent relation, corresponding row. But if all three are satisfied, then it is called an equivalence relation. So, what is the example of an equivalent relation? Like is less than equal to is equivalent relation? Let us try that. Suppose our S is R and we define this relation, say A B if A is less than B. So, is this an equivalent relation? Is this symmetric? First of all, it is not symmetric unless we put a less than equal to. But is this a is this a reflexive? Unless we put a less than equal to, it is not reflexive. So, now if we put a less than equal to, it is reflexive, but it is not a symmetric relation, because 1 3 belongs to row, but 3 1 does not belongs to row, because 3 is not less than equal to 1. So, that means it is not a symmetric relation, although it is a transitive relation. So, but since one properties is not satisfying, then it is not a equivalence relations. Okay, then what is the example of equivalent relation? Now, suppose we take this relation, say we are in S is Z, set of all integer. Now, we define a binary relation like this, A B coming from Z Cartesian product, if A minus B is divisible by 5, divisible by 5, number 5. Okay, we define this relation if A minus B is divisible by 5. So, now we have to test the whether this relation is an equivalent relation or not. So, now for this, if we take A B, A, first we have to take the reflexive, whether this is a reflexive relation or not. So, how to do that? Suppose we take A. So, A means what? A minus A is 0. So, 0 is divisible by 5, which is divisible by 5. So, A is belongs to rho for all A. So, this is reflexive. Now, is this symmetric? That we have to check. So, now we can check the symmetricity. So, symmetric means if we take A B belongs to rho, then we have to prove, we have to show B A also belongs to rho. So, A B belongs to rho means A minus B is divisible by 5. So, A minus B is basically some k into 5, where k is an integer. Now, we need to show that B minus A also must be a B minus A also divisible by 5. What is B minus A? If we take, then B minus A is nothing but minus of k into 5. So, this is another k prime into 5. So, yes, B minus A is divisible by 5. So, B minus A is divisible by 5, or 5 divides B minus A, if we use that symbol. 5 divides B minus A, this symbol we use for divides. So, if A minus, so that means A minus 5, if 5 divides A minus B, this implies 5 divides B minus A. So, this is symmetric. So, that means for all A B belongs to rho imply B A belongs to rho. So, this is the symmetricity. Now, we need to check the another property, which is called transitive property. This is the third property, transitive. So, for transitive property, we need to take A B, B C. A B belongs to rho, and also this is rho, sorry, and B C belongs to rho. We take A B and B C arbitrarily, any, this is for any A B C. Then we have to show that A C also belongs to rho, then that is the transitive property. So, how to show that? A B belongs to rho means what? That 5 divides A minus B, and B C belongs to rho means 5 divides B minus C. Now, if 5 divides B minus 5 divides A minus B means A minus B is equal to some k 1 into 5, and B minus C is equal to some k 2 into 5. Okay. Now, what we can write here? Okay, now, what is, if we add these two, then A minus C will we get k 1 plus k 2 into 5. So, this implies 5 divides A minus C. So, this implies A C belongs to rho. Okay. So, that means, if you take any two element A B and B C, if they are in rho, then A C belongs to rho. So, this is the transitive property. So, we have seen, so this is the transitive. So, this relation is satisfying both reflexive, symmetric and transitive. So, this is an equivalence relations. This is an example of an equivalence relation. Now, we can take another example, like we can check that relation we had earlier, that A plus B is even, whether that is equivalence or not. So, we take a row which is basically A B, B is even. So, can you check whether this is equivalent? First of all, this is this reflexive? Yes, it is reflexive, because A plus A is 2A, which is even, which is always even. So, A comma A is belongs to rho for all A. Yes, reflexive. Now, is this symmetric? Yes, because if A plus B is even, then B plus A is also even, because this plus is commutative. Commutative means A plus B is same as B plus A. So, the value is having same value. This is the real number plus. Now, transitive, if AB belongs to rho and BC belongs to rho, we need to show that AC belongs to rho. So, AB belongs to rho means A plus B is even. So, A plus B is some 2 k 1 and BC belongs to rho means B plus C is 2 k 2. Now, if you subtract these two, k 1 k 2 are two integer, but A plus B. So, this need not be A plus. So, how to show from here that A plus C is even? We have to show this is some k 3. So, like if we take say 1 comma 5 and 5 comma 5 comma say 7, then 1 comma 7, but is this easy to show? Can you check that whether A C, how to check that A C is A plus C? So, if we just add these two, then A plus 2 B plus C is equal to 2 of k 1 plus k 2. Yeah. So, now A plus C is basically 2 of k 1 plus k 2 minus B. Yes. So, A plus C is even. So, this is a transitivity property is also satisfying. So, this is a equivalence. This is another example of an equivalence relation. So, we will talk about more on equivalence relation in the next class. Thank you.